chapter 1, so this is not like something that we are going to try to accomplish all of it today. My dream is to get through section 1-1, but I don't know if that dream is going to be realized or not just because we had that meeting. So my hope would be to get to here, but if we don't make it, we don't make it, and we'll come back to this another day. All right, we're going to talk about different types of numbers, and I'm sure you've had these conversations before, so this shouldn't be the first time you're hearing this. It's probably going to be a review. You'll find a lot of the first couple chapters in pre-calc are review of stuff you've done in Algebra 2 or 2H. It's just going to kind of build off of the things that you've already done and go probably a little more in depth. Okay, natural numbers. We also call these the counting numbers. So think about when you count. What's the first number you count with? 1. Okay, so we don't start at 0 typically. We don't start at like -1. So counting numbers, 1, 2, 3, 4, 5, 6. So they are what we would call our positive integers. And they would include 1, 2, 3, 4, and then so on. Remember that these notes are for you. I'm never going to come around and inspect them and make sure that you've written down everything that I did. If you have 5 dots after the comma, I don't know, should I check that? No, I'm not going to. So make sure that you write down what's meaningful to you. If I use some words that you're like, oh, I don't love her wording, put it in your own words. So you're writing down stuff in the notes that's meaningful to you. And again, remembering that I'm never going to check these in. These are not a grade. These are not any of that. Okay? So making sure that they're there for you to support you as you study for quizzes and tests and anything else. Okay, so we've got these positive integers. So what are integers in general? Integers in general are going to be the natural numbers that we just talked about. Oops, I spelled it wrong. Pretend I did it. Natural numbers. The number 0 and the negatives of the natural numbers. So we would have a bunch of stuff, and then I'll start at -3 in terms of what I'm just going to write as examples. So we would have all sorts of negative numbers, and then -3 would be another integer, -2 is an integer, so is -1, so is 0, so is 1, 2, 3, and then we go into the positives from there. So again, we're not looking at decimals, we're not looking at fractions that wouldn't divide out to a whole number, like we are just negatives, positives, and 0, and again, we're not looking at any decimal here. Now, often when we refer to integers, we call them by the letter Z. I don't have a good reason why, but we use Z to stand for the set of integers. Now, do you remember before doing the set of real numbers? How do we write it? If I wanted to write the set of real numbers, what would I write? Remember? An R, and then what else though? With an extra line, right? So that's the set of all real numbers. So that's not including anything that's imaginary, like if we're square rooting a negative number. So for integers, just like this has the extra line through it, the Z gets an extra line right here. So this symbol means the set of integers. So this means the set of integers. Now, one thing you're going to notice about me throughout the year is that I get nervous when I write Z's. What number am I worried you're going to think that is? 2. So I cross my Z's. So if you want to do that too, you can. You do not have to, but just be aware that I'm always going to cross my Z's. So I'm going to put that in there. You do not need to. Okay, so that's going to be me all year long, so you know the difference between my 2's and my Z's. And you're able to tell those pretty easily. All right, rational numbers are are numbers that can be written as fractions. Numbers that can be written as fractions. So this actually includes a lot of things. So it includes stuff like 1/3. Is that written as a fraction? Sure is. What if I did 0.6 repeating? So I put the little cap over it. Is this also something that's fractional because it can be written as a fraction? Yeah, what's its fraction form? 2/3. Another one would be like 0.25. What fraction is that? 1/4. Another thing that we probably don't think of as being a rational number, but it is the number 5 or 6 or 7 or any of those numbers. Because can I put that over 1 and it's a fraction? Yeah. So all of our integers are going to fit in here too because we can divide by 1. Does that make sense? Okay. Always feel free to stop me, raise your hand, say something if something doesn't make sense or you have a question. I don't find notes like super formal in the fact that like you must be silent. Like obviously I want you quiet and listening, but if you have stuff that you need to know, shout it out. Alright, so irrational numbers are numbers that cannot be written as fractions. So you cannot be both rational and irrational at the same time. You're one or you're the other. You can't be both. So irrational numbers. You probably know the number friend pi. Pi is an irrational number. So irrational numbers are decimals that go on forever and ever and ever. And one thing that's kind of special about them is that not only do they go on forever, but they don't repeat. So for example, this decimal goes on forever, but it repeats. That's why it's a fraction and a rational number. Pi doesn't repeat. So they never terminate, meaning they never stop, they never end, and they also never repeat. We should have also seen a new number from last year. Did we meet E? Okay, like natural logarithms, log to the base E was ln. That's another irrational number. The other things that are irrational numbers are ugly square roots. And when I say ugly square roots, I mean things that when you go to square root it, it doesn't come out nice, like 2. So the square root of 3 would be an irrational number. It's not something that can be written as a fraction. How are we doing so far? Okay? I'm going to keep checking in. So down here at the bottom, you can kind of see a picture of all of this going on and how they interact with each other. So whole numbers, we didn't talk about that up above, but whole numbers would be the 7 natural numbers and also 0. You can see how everything kind of fits in together. And then truly, off to the side in its own little world, could I do imaginaries over here? So these are imaginary / complex numbers would live over here. So they don't live in this world of real numbers. So here's our real number system, and the imaginary complex numbers would live over here. Sometimes it's just got an imaginary component like 5i. Or sometimes it's a combo. So complex numbers are a combo of real and imaginary. So if you had something like 4 or 3 plus 4i, that has got a real component, the 3, and then an imaginary component as well. So these live separately from each other. It can't be real and imaginary, it's one or the other. Alright, flip when you're ready. Keep on going. We're going to talk about a couple properties. Again, that you probably should already know, but we're going to continue talking about them. Alright, commutative property. So commutative property can come at you in a couple different ways. It can be an addition property or it can be multiplication. So this could be addition or it could be multiplication. What it basically says is that you can switch the order and it's still going to give you the same answer. So you can switch the order. And still get the same answer. And I'll show you what I mean. That's a little vague. Alright, so for addition, let's start with addition. If I had 5 plus 4, that gives you 9. If I flip them and I go in the opposite order and I go 4 plus 5, what am I going to get? 9. So that's the commutative property. So it's telling me that I can add them in either order and I'm going to get the same number. Same thing with multiplication most of the time. There's a funny example at the end of the year when we get into matrices where that's not going to uphold, but 99% of the time multiplication upholds as well. So if you were going to multiply, 2 times 3 is 6. And if I flip them, 3 times 2 is also 6. Okay, so those can be flipped and it's still going to work. Associative property is very similar, except instead of 2 things, we can switch the order of 3 or more things. So again, associative property works for addition and multiplication. And the way I word it, it's the same as the commutative property. But with 3 numbers. Not sure what I was going to write here, but with 3 numbers. There we go. So for example, if I did 2 times 3 times 4, bless you, or if I did 2 times 3 with the 4 outside. So think about PEMDAS for a second. I have to do what's in parentheses first, right? PEMDAS still applies to everything. So for this problem, I would do 3 times 4 first, which is 12, times the 2 is 24. Here, it's telling me to do this first. So 2 times 3 is 6, times the 4 is 24. So again, associative property is very similar to commutative property. It's just going to be with 3 numbers. Now, I'm never going to quiz you on this and say, hey, I just used a property. Which one was it? You need to know that these work, but you're never going to be quizzed on the names. And then distributive property, we probably use that a ton. So that's when you multiply into a set of parentheses. So you have a set of parentheses and you're multiplying in. The thing you're multiplying in could be out front, so it could look like this. Or it could even be out back and look like this. So it doesn't matter if it's out front or out back. When you've got distributive property, you're taking whatever's outside and you're multiplying it in if there's no symbol separating it from the parentheses. So what would I get for the top one? Yeah, 4x squared plus 20x. And in the bottom, same thing, even though it's out back, what do I get? 6x minus 30. Okay, so just some of those basic math skills, and yes, I know we're taking it way back and way simplified, but we got to start somewhere. Alright, the next thing I want to talk to you about is how to give answers. So typically in this class when we give answers, we give them in what's called set notation, and sometimes we call this interval notation. So those are interchangeable. So if you hear me say set notation or interval notation, this is what I'm going for. Okay? So the set notation is here, and then the interval notation, the way it looks, is going to go right here. So set notation, let's start with this one. I'm going to write it out and then I'm going to explain it. I think that's going to be easier. So go ahead and copy what I'm writing. And then I'm going to go through and explain what I'm writing. There's a lot going on here. Okay. So this first column is my interval notation. The second column is my set notation or set description. So they're two separate things, but they're referring to the same thing in the fact that you're giving a set of answers. Okay, so when you're giving a set of answers, you can give your set of answers in set notation or interval notation. They look different, but they're both doing the same thing. They're giving you your solutions. If you have a solution like this where it tells you A to B, that means that all the solutions that live in between A and B work. So if you had 4, 7, that would tell you all solutions or all numbers between 4 and 7 work. When you have this open parenthesis like that though, it's not going to include the end. So if you had that as a solution set, it would tell me between 4 and 7 are solutions, but 4 and 7 themselves are not included. So a parenthesis means that number itself is not included. So if you look over here, so again, we're kind of in math language today. We're writing a lot of math symbols. This means X such that X is going to be smaller than B and bigger than A at the same time. And if I think graphically, like what's it going to look like? Open circle at B, open circle at A, shaded in the middle. So again, we're not including A and B, whatever those might be equal to. Remember, A and B are just standing for a number. So whatever A and B are, doesn't matter. These two are not included, but everything in between is. And this will make more sense as we see a couple more. So do you see now how we have switched to brackets? Okay, so they are both brackets. So here's what's going to change for this. X such that A is less than or equal to X is less than or equal to B. So brackets tell me that A and B are included. Open parentheses tell me that it's not included. So brackets included, parentheses not. So when I go to draw my graph, here's A, here's B, close circle at A, close circle at B, shaded in the middle. So we're kind of connecting 3 ideas here. All of these are giving me solutions, right? It's telling me the solutions, but it's giving it to me in different ways. It's giving it to me in interval notation, then it's giving me in set builder or set notation, and then it's showing me with a picture or a graph how my solutions are given. So when you get to homework, you'll have to read and see like what it's asking you for and make sure that your answer corresponds. All right, let's look at the next one. Do you see how the A has a bracket and the B does not? So we've got to honor that. X such that A is less than or equal to X. What am I going to put next? Is less than B. And then we're going to close it off. So when I go to make my graph, what kind of circle am I going to have at A? Closed. And at B? Open. And again, this is important when we go through and look at solutions to see what's included and what's not. Okay, you try the next one. I think you can do the next one without me. It's almost identical, but we got to flip. So try that one for me. I'll pull mine down so you can't see. Take a look at mine when you're done. Make sure you agree. Are we matching? Notice that whenever we have infinities, it's always going to be a parenthesis. Because I feel like the way I explain it best is when you go to the number 5, you can reach out and touch the number 5. But is infinity something you can ever like arrive at or reach? No. And so that's why infinity is always going to get a parenthesis no matter what. So every time you see an infinity, there will always, always, always be a parenthesis on the other side of it. If it's negative infinity, it'll be over there. But again, either side, whether it's negative or positive infinity, will always have a parenthesis. So let's talk about this one. X such that. So this is saying we start at A, but is A included? No. So A is not included. We're starting just after that, and we're going to infinity. So the way that I would write this is that X is going to be greater than A. It can't be equal to A because of the parentheses, but it can be anything bigger. So on my number line, I'm not going to have an A and a B this time. I'm just going to have an A. Open or close circle at A? Open, because we're not going to include A. And then which way should I shade? To the left or to the right? To the right, because we want all the things that are bigger than A, and our bigger things live to the right. Our negative things and smaller things live to the left. So typically when I'm doing this type of problem, I like to just kind of shade in even a little bit more and kind of really show like, okay, this part of the graph. Okay, the next one is very similar. What's the only change you see? It's a bracket. So X such that X is what? Greater than or equal to A. Alright, so I think you guys have got this. I'm going to have you try to fill out the rest of the chart on your own, and then we're going to double check and make sure we match up, okay? So you keep filling it out, fill it out down to the very bottom. I'm going to keep going too, and then we'll check back in and make sure we've got this. But I think we do. Maybe don't do the last one though. Stop before you get to the last one. The last one's a little funny. And maybe you already know how to do it, and that's great. Go ahead if you do, but that one's a little bit different than all the rest. I'm going to put mine back up in the field of vision in just a second so we can talk through it. We might actually make it through everything. This is awesome. Up when you're ready. Spoiler alert is on the board. So for the B's, it's going to be less than, so it's going the other direction. Again, be careful with your open or closed circle depending if there was a parenthesis or a bracket. The very last one. Do you see how I shaded the entire thing because it's all the numbers? Okay, so how do we write all the numbers? So X such that X exists. So this is like a C, like a curvy E with a line through it. That's our E for exists in math. And this language that we're using is going to be consistent forever. So I went to Michigan State. I took through Calc 4, and then I got to take 17 math classes after Calc 4 to get to my math degree. Doesn't that sound like a good time? Yes. And so when I saw set notation at Michigan State, it's the same. So the good news is you're not going to go off to some college and have to learn a new notation. Like, this is our accepted notation. Does that make sense? So there's not going to be like, and now you're here and we actually do it this way. No, there's no other way. That's the same notation I used in college. Good? Okay, flip when you're ready. Okay. Now we're going to try to graph them out in space. Okay? The first one tells me -5 to 3. Open or close circle at -5. Close, open or close circle at 3. Open. And then we're going to shade in between because it's telling me that's where my answers live. Alright, let's make another one for number 2. And again, we're just depicting where answers live. I only need one thing for this number line. What do I need on there? 1/4, which is a rational number. Open or close circle at that rational number. Closed. And which way should I shade? To the left. Negative infinity is this way. Positive infinity is the other way. Ooh, now we have some U's. A U and then an upside down U. Okay, do we know what the U's mean? Okay, this U means union. The best way that I can explain it is if you move off to college and you take all your stuff, and then your roommate moves in and they bring all their stuff, all the things in your room are the union. You have your stuff, their stuff, the union is all the things. Now, you go off to college and you bring your stuff. This is the next one down. This is the intersection when you have the upside down U. You go off to college and you bring your stuff. And your roommate brings their stuff. And you both have the same Michigan State poster. That's the intersection. The intersection is what you have in common. So the union is all the things. The intersection is what you have in common between the two. So let's take a look at this one. So this one is asking for both. So it's saying that we are going from 1 to 3, and we're also going to go from 2 to 7. So this is also something we associate with the word and, whereas this one we associate with the word or. It's one or the other. So if I can be 1 to 3 and 2 to 7, do you see how those overlap? So truly, if I could be a number between 1 and 3 or 2 and 7, could I be all the way to 1 to 7? Okay. And now, because it's both included, I need to think about my sign. So we were a parenthesis at 1, and then we were a bracket at 7. So open all the way up. So again, think about it like you're bringing your stuff to campus. You bring 1 to 3, your roommate brings 2 to 7. What do you have in the room with you? You have all the numbers between 1 and 7, stopping at 7. Here we're looking at what we have in common. So think about your numbers, and let's just think about integers for a second. What integers live in this little window? Just 2, right? So we really got 2 because do we actually include, like 1 and 3 would be in open circles, and like it would be something like this. Okay, think about 2 to 7 now. You'd have a closed circle at 2, you'd have a closed circle at 7, and you'd include everything in between. What parts of that overlap? Like live in both? The 2, which would be included, right? It'd be included here and here, up to 3. Now is the 3 included here? On the left side? No. So it's not going to be included overall. So what am I going to have? I'm going to have 2 to 3. The 2 is included. The 3 is not. So again, think about you move into college and you move in with all these numbers, 1 through 3. Even all the stuff in between it, like 1.75. You move in with all this stuff. So you have 2 to 3. Your roommate also has 2 to 3. But we can't include 3 here, so we can't include it overall. So if it's included in one but not the other, we can't have it be for both. It can't live in that intersection. It's a hard one to think about. Go down to the true and false. What do we think about the first one? It is true. So if you take the absolute value of the whole thing versus individually, we're going to get, it's going to be the same. What about number 2? That they are not equal. It's false, because they should be equal, right? How about number 3, looking at the absolute values? Will they be equal? Yeah, they will be equal. What about number 4? The distance between two numbers on a number line is a minus b. At first glance, you probably want to say true. It's actually going to be false. The reason being is distance ever going to be negative? No. And if you subtract a minus b, sometimes that could give you a negative number. So instead of this, we actually need this. So remember, distance is always positive when we think about that in terms of absolute values. Okay, we did it, people. I'm going to tell you what homework is. Show your work, do it on a sheet of paper, on a sheet of notebook paper that I can look at and check in on Monday. Ooh, I didn't grab parent letters. I will grab parent letters and homework on Monday. Sound good? Okay. So this is assignment number 1. Each chapter I start over fresh, from scratch. So we are on assignment number 1. We are page 9 through 11 in your textbook. Remember, you can use your actual hard copy of your textbook, or you can open up the online version that's available in Skyward, or not Skyward, Google Classroom. I would like you to do, please, oh, that's the wrong one. Sorry, people. Oh, I already have screwed this up. Page 10 through 11. 10 through 11. I was close. I was looking at Algebra 1. I'm so sorry. We're going to do 20 through 32, the evens. We're going to do number 40. We're going to do 46 to 58, the evens. And then we're going to do 66 to 70, the evens. So again, this is the practice to go along with what we just did. So your notes should come in handy and help you out. So make sure you use those and have them with you to help do the homework. So I'm going to check this in on Monday, and I'm going to collect parent letters on Monday, both of things. Sound good? Usually we have some time to start homework. Today is not that day because of the class meeting. So thank you for rolling and going super fast, Ellie. So that whole